Multiple linear regression is an expansion of simple linear regression where you have more than one predictor variable. So you still have one outcome variable that you're predicting. You're just saying that there's more than one predictor variable that we can use to predict that outcome variable. And the measure that you'll see with multiple linear regression is a capital R squared. That's the overall coefficient of determination. So it's always going to be reported. It ranges from 0 to 1. And this is capturing how much of the variation in this outcome variable is explained by this entire equation. Sometimes you'll see an adjusted R squared. And all they're doing there is taking into account how many of these predictor variables they have. So just because of the math, the more predictor variables you have, the better your Y, your prediction, is going to be. So it never gets worse by adding in more predictor variables. So this adjusted R squared compensates for that. They may report or will report the betas for the individual predictor variables. And it gets a little confusing because with simple linear regression, it kind of makes sense. If I have a change in my X, that's going to lead to a change in my Y. When I've got multiple predictor variables, multiple X's, what they're saying is if we held all of those other predictor variables constant and the only thing we changed was one unit of this one predictor variable, we'd get this big a change in the outcome variable. More often, people are reporting confidence intervals. Sometimes you'll see standardized betas, and here what they're correcting for are different units. So if you've got one unit is dosage in milligrams and another unit is time in days, using standardized beta corrects for the fact that you're using different units in your predictor variables. So when you've got correlation, what you're looking at is R, the correlation coefficient, and that ranges from -1 to +1. If you have simple linear regression, you'll see a lowercase r squared, and that ranges from 0 to +1. If you have multiple linear regression, you'll see a capital R squared. It also ranges from 0 to 1. Here's an example of a paper from AJOT. And you can see they used the standardized coefficients. So they've got predictor variables with very different units: gender, measure of pain, and physical abilities. So those are totally different units. They've standardized the coefficients. They did not say whether they used the adjusted R squared. So if they don't say they used adjusted R squared, I would assume they just used regular R squared. And the way this works, psychosocial adjustment, that's what they're predicting. So that's their Y. Each one of these is one of their X's. And these are the different betas that go with those different X's. Here's some text from another paper in AJOT. And what they're saying is, first, they used univariable models, and then they built a multivariable model. And then they went back and looked at whether adding these models in changed their their Bs or their betas. So that's a lot to take in. What they're saying is that the first thing they did was they made a whole bunch of simple linear regressions. Those are their univariable models. So each one of these is y equals, this is the beta times x. And they did it with just one individual variable. And then in step 2 and step 3, that's where they created one big linear regression, multiple linear regression. So this is 1y equals all of these different betas times their respective x's. And this r squared, you can see they use the adjusted r squared. That's accounting for how many of these predictor variables they have. But interestingly, they don't say that they used standardized beta coefficients. So you don't know whether they're correcting for these different units, right? So unit of residence, whether or not they had a mentor, years in as an occupational therapist, those are totally different units. They're not saying whether these betas take that into account.